Think about the last time you kicked back to watch a movie. You hit play on a 4K stream and boom, it just works. The picture's perfect, the sound is amazing, and there's zero buffering. It honestly feels like magic. But as you can probably guess, it's not. Behind that seamless experience is an incredible stack of engineering brilliance. And today, we're going to pull back that curtain and see how it all really works. So this is really the core question, isn't it? How does something that needs to be so perfect, like a high-definition video, travel over an internet that was built on a best effort principle? And best effort means exactly what it sounds like. The network tries its best, but it doesn't actually guarantee your data will arrive on time, or in the right order, or even arrive at all. It's a pretty chaotic place. So how in the world do we get such perfect, smooth results? All right, let's dive into the first big piece of this puzzle. We're going to start by looking at the challenge of streaming pre-recorded content. Your favorite shows on Netflix or that video you're watching on YouTube. The name of the game here is delivering a smooth, uninterrupted experience. And the main villain in this story, the enemy of smooth streaming, has a name: jitter. See, the internet doesn't send data to you like a smooth, flowing river. It sends it in little packets. And those packets don't arrive at a perfectly constant rate. Some show up a little early, some show up a little late. That unpredictable variation in arrival time, that's jitter. And it is the technical culprit behind that dreaded buffering wheel we all hate to see. So, how do we defeat this villain, jitter? Well, with a surprisingly simple yet brilliant hero, the client-side buffer. The easiest way to think about this is to imagine a water tank. The internet is filling up that tank. But because of jitter, the water comes in spurts, sometimes fast, sometimes slow. But your device, your TV or your phone, is draining water from a tap at the bottom at a perfectly constant, steady rate to play the video. That buffer, that tank of data, acts as a shock absorber. As long as there's some data in it, your playback stays perfectly smooth. It's the whole reason a video has to load for a few seconds before it starts. It's just filling up the tank.
Right, so that buffering solution is genius, but it only works for pre-recorded stuff. What about a live two-way video call on Skype or Zoom? Well, that is a completely different ballgame with a totally different set of problems. In fact, the priorities are completely flipped on their head.
For conversation to feel natural, to feel human, the total delay from when one person speaks to when the other person hears it has to be incredibly low. All the research shows that once that delay gets above this number, about 400 milliseconds, which is less than half a second, our brains really start to notice. The conversation just feels off. It gets awkward, we start talking over each other, it all just falls apart. And this right here is the fundamental trade-off. For Netflix, the main goal is uninterrupted playback. So we're totally fine with a big initial delay to fill up that buffer. But for Skype, the goal is immediacy. You absolutely cannot have a big buffer because that would add seconds of delay, making a real-time conversation impossible. So get this, the very thing that saves streaming video, that big buffer, is the exact thing that would kill a video call. So, if a big buffer is off the table for live calls, what's left? What's in the engineer's secret toolkit to solve this problem? Well, they have a whole bunch of specific protocols and really clever tricks that they use to make it all happen. Let's take a look. First up, and this is the absolute cornerstone, is RTP, the real-time protocol. Think of it as a super precise timekeeper for every single tiny packet of audio and video. It adds a special label to each packet that has a sequence number and a timestamp. Why is this so important? Well, remember, packets can get lost or arrive all out of order. The sequence number tells your computer how to reassemble the puzzle in the correct order, and the timestamp tells it the exact moment to play that piece of sound or show that frame of video. It's what brings order to all that network chaos. Okay, so RTP is amazing for handling the media during the call. But how does a call even start? That's where SIP comes in, the Session Initiation Protocol. You can think of it like a digital handshake. When you call someone, SIP is the protocol that finds their device out there on the internet, makes it ring, and then helps your device and their device negotiate the rules of the road. Things like what video quality can you handle, or what audio format should we use. It gets all that setup work done before you even get to say hello. Now, this is one of my favorites. It's a really clever trick called forward error correction, or FEC. See, in a live call, if a packet gets lost, you just don't have time to ask for it to be sent again. That would take way too long, and you'd get a big glitch. So instead of reacting to a problem, FEC anticipates it. It proactively sends a little bit of extra redundant data along with the mainstream. For instance, for every 4 packets of audio, it might send a special 5th summary packet. If one of those original 4 gets lost,
the computer on the other end can use that summary packet to mathematically rebuild the missing one instantly. No waiting, no glitch. It's pretty brilliant.
So we've covered all these cool tricks that our devices are using, but that's only half the story. The internet itself is also getting a lot smarter. We're slowly moving away from that purely best effort, anything goes model to a much more organized and managed system.
And the core idea behind this smarter internet is actually really simple. Not all data is created equal. A packet for your real-time Zoom call is way more sensitive to delay than a packet for a file download. So to make everything work smoothly, the internet really needs a VIP lane, an express lane, just for this time-sensitive traffic.
And at the same time, all the other data that isn't in a rush, your emails, that big software update, it can take the scenic route. It can hang out in the standard lanes. It'll still get where it's going, it just doesn't need the red carpet treatment. Now, this whole VIP lane system has a technical name, Quality of Service, or you'll often hear it called QoS. It's basically the traffic management system for the internet. Instead of treating every packet the same, QoS is the set of rules and technologies that lets network operators create these different priority levels, making sure the most critical data gets the fast-track treatment it needs. So how does this actually work in the real world? Well, a common method is called differentiated services. It works in a few steps. First, as that voice packet leaves your home network, the router marks it with a special code that basically screams, "I'm high priority." Then, as it travels across the internet, the big core routers read that mark and put the packet into a special high-priority queue. Think of it like the express checkout lane at the grocery store. Finally, the router's scheduler is programmed to always serve that express lane first. This ensures your time-sensitive packets get to jump the line and get through with the absolute minimum delay. So, when you put this all together, from the buffer on your phone to the VIP lanes on the internet backbone, you start to see the bigger picture. That seamless stream you're enjoying isn't magic at all. It's a sophisticated toolkit of really clever engineering solutions. Buffers, real-time protocols, error correction, smart network management, all layered on top of each other, all working together to create perfect order out of the internet's natural chaos. And that brings us to the future. I mean, we've pretty much figured out how to make 4K video and video calls work incredibly well. But what happens next? As we push towards 8K streaming everywhere and truly immersive, real-time virtual and augmented reality, the demands for bandwidth and super low latency are just going to be astronomical. So the question to leave you with is this: what new, unforeseen problems are going to pop up? And what incredible new tricks will the next generation of network engineers have to invent to make that future feel just as seamless?